Hey guys, welcome back to Fun Paradise. Today we're going to be talking about dark matter and dark energy. Before we get on to the video, hit that subscribe button and ring that bell if you haven't already so that you get notified whenever we upload a new video. Dark matter is composed of particles that don't absorb, reflect, or emit light, so they cannot be detected by absorbing electromagnetic radiations. Dark matter is material that cannot be seen directly. We know dark matter exists because of the effect it has on the objects that we can see directly. Dark energy is a mysterious force that's causing the rate of expansion of our universe to accelerate over time rather than to slow it down. Dark matter and dark energy are like the yin and yang of the cosmos. Dark matter produces an attractive force, while dark energy produces a repulsive force. It turns out that roughly 68% of the universe is dark energy. Dark matter makes up to about 27%. The rest, everything on Earth, everything ever observed with all our instruments, all normal matter adds up to less than 5% of the universe. One explanation for dark energy is that it is a property of space. Albert Einstein was the first person to realize that empty space is not nothing. Space has amazing properties, many of which are just beginning to be understood. The first property that Einstein discovered is that it is possible for more space to come into existence. Then, one version of Einstein's gravity theory, the version that contains a cosmological constant, makes a second prediction. Empty space can possess its own energy. If energy is a property of space itself, it would not be diluted as space expands. As more space comes into existence, more of this energy of space would appear. As a result, this form of energy would cause the universe to expand faster and faster. Unfortunately, no one understands why the cosmological constant should even be there, much less why it would have exactly the right value to cause the observed acceleration of the universe. Another explanation for how space acquires energy comes from the quantum theory of matter. In this theory, empty space is actually full of temporary particles that continually form and then disappear. But when physicists tried to calculate how much energy this would give empty space, the answer came out wrong. Wrong by a lot. Another explanation of dark energy is that it's a new kind of dynamical energy fluid, something that fills all of space with something whose effect on the expansion of the universe is the opposite of matter. Some theorists have named this quintessence, after the fifth element of Greek philosophers. But if quintessence is the answer, we still don't know what it's like, what it interacts with, and why it exists. A last possibility is that Einstein's theory of gravity is not correct. That would not only affect the expansion of the universe, but it would also affect the way normal matter in galaxies and clusters of galaxies behaved. This fact would provide a way to decide if the solution of dark energy problem is a new gravity theory or not. We could observe how galaxies come together in clusters. But if it does turn out that a new theory of gravity is needed, what kind of theory would it be? How could it correctly describe the motion of the bodies in the solar system as Einstein's theory is known to do, and still give us the different prediction of our universe that we need? There are candidate theories, but none are compelling. The thing that is needed to decide between dark energy possibilities, a property of space, a new dynamic fluid, or a new theory of gravity, is more data, better data. We are much more certain what dark matter is not than what it is. First, it is dark, meaning that it is not in the form of stars and planets that we see. Second, it is not in the form of dark clouds of normal matter, matter made up of particles called baryons. We know this because we would be able to detect baryonic clouds by their absorption of radiation passing through them. Third, dark matter is not antimatter, because we do not see the unique gamma rays that are produced when antimatter annihilates with matter. Finally, we can rule out large galaxy-sized black holes on the basis of how many gravitational lenses we see. High concentrations of matter bend light passing near them from objects further away. But we do not see enough lensing events to suggest that such objects to make up the required 25% dark matter contribution. However, at this point, there are still a few dark matter possibilities that are viable. Baryonic matter could still make up the dark matter if it were all tied up in brown dwarfs or in small, dense chunks of heavy elements. These possibilities are known as machos. But the most common view is that dark matter is not baryonic at all, but that it is made up of other, more exotic particles like axions or WIMPs. What are your thoughts on this? Make sure to tell us in the comments down below. Also, don't forget to subscribe, like, comment, and share. We also have a Discord server, so if you want to check it out, I'll leave the link in the description below. I'll see you guys next video. Bye!